we are going to continue with xTensor today. I'm going to switch my tutorial on Monday, from Monday to, I'll do it on Tuesday, Wednesday, and Friday. So on Tuesday, I can start with Xcoba, and Wednesday, I can get into this variation of the action to get the field equations. And finally, on Friday, we can do some perturbation, black hole perturbation, black hole stability studies. Let's see how it goes. Okay, so we have 2 minutes. Anybody tried anything? Like some calculations that you guys are doing? Okay. All the tutorials that you get, you can try to do the same tutorials once you calculate all these things by hand, see whether you can do the same thing. So I'm not giving you, there are certain challenge questions that I keep at the end, but I'm guessing this has already been done in the other tutorials. Again, I'm not trying to teach anything new, I'm just trying to teach, what I'm trying to do is get into the habit of doing the same problem, which you already know how to do it by hand. Try to do it using these packages. Okay. There are a number of things, this is always a work in progress, so there's a number of things which is not defined, and today we will learn about how to make rules, and that is very important, and that is why you should always know how to do the basic calculations by hand, so that you have the intuition to make the correct rule. Okay, and only if you make the correct rule, the things simplify, and you can do your calculations fast. So it's not like don't treat this like a black box. Nothing is going to work as a black box. Okay, so understand the rules properly. Understand what you have to put as a rule. Okay, we can start. Okay, so as I said, this is an extension of the previous sort of tutorial. So now these are things which you now know. How to load the package, and this is obviously something that you have to do. Remember to put this screen dollar indices. If you don't do it, I don't know whether you have tried without using it. Yeah, sometimes when you compute, you will get a lot of garbage values as indices. So rather than like how we have defined the indices to be A, B, C, D, E, F, whatever, you will get some garbage dollar values. So to get rid of that, so you can either, everywhere you are getting this, you can put something which is called as screen dollar indices, or you can just put this so that you never get this. Okay, so we have to again define the manifold. These are things that you know. We have to define a bunch of tensors. So these are things that you have already seen before. Now, there was a question last time about the symmetric, anti-symmetric. Did you figure it out? Whoever asked the question?
It will be symmetric.
Is it? I thought like there would be no relation.
Because if you do those in anti-symmetric, it will give 0.
Mm-hmm.
So that will be not 0 if you don't define it.
Okay. I thought like this sort of rule is not going to be given if you by default, but maybe symmetric is the default. Okay, I have not checked that. Thanks. Okay, so you have to define a bunch of tensors and obviously a metric. So nothing new about this. We did talk about Riemann tensor last time. So I think we are going to now talk a little more about its symmetries.
So again, this is how you are defining a Riemann tensor. And now I want to define something like this, okay? Quantity like this. So using all the one form tensors. Now, there are two different things for Riemann tensors. One is you have symmetries over one of the indices, or you have symmetries over pairs of indices. Okay. So this, if you're doing symmetries over one of the indices, you're taking one index and trying to look whether it's symmetric or antisymmetric. These are called monoterm symmetries. Okay. Now this is simple in xAct. Monoterm symmetries are simple. What you will see is multi-term symmetries are generally complicated. And if you look at the documentation for xTensor, there will be a section which talks about this multi-term symmetries. Right, so monotone symmetries, again, I think maybe we discussed this last time as well. So here what I'm doing is, this is my term, right? Now if I'm just writing this, then in principle this should go to 0, right? But you have to take the canonical form, so you have to use this 2 canonical, and the inbuilt symmetries there will be used, or the rules are going to be used, and you get 0. So is this term clear to you? Like if this particular expression should go to 0, is this something which you guys understand? Okay. Can anyone tell me why? Maybe. Again, what property is it? What property of the Riemann is this using? You know this. Come on. Huh? In here, in which indices is it? Yeah, exactly. Thank you. So that's what it's using here, the antisymmetric in this AB indices, and that's why this goes to 0. Now, what are the, if I'm talking about pairs symmetries, what are the Riemann pair symmetries that you know of for a Riemann tensor? Right. So if I write this expression, can you tell me what it should become? Zero. Right? Now, see the same thing, if I do 2 canonical, that's not going to 0. So that's why I said monotone symmetries are easy for xAct to apply, but not for multiterm symmetries. So what I'm trying to tell you is, you have to know the math, right? You can't just blindly use things. And there are obviously some packages, and there will be problems in the packages, but it's going to help you in many ways, but somewhere it might default or create a problem, and you should know those things as well. Right, so if you know this, you can always set a rule saying whenever something like this comes, I know this is 0, so set it to 0. Okay, so that provision of making a rule is always there, and that we are going to show at the end. But what I want to drive is, it's not like it's so simple that, oh, everything is going to work for you, right? So you should know the steps. Okay? So, so this is not working. So even if I tried this simplification, which includes something like the 2 canonical, it's not going to 0, right? So this is a thing, like you can check section 9.2 of this xTensor doc. And this talks about this multi-term symmetries of Riemann tensor. Okay, so let's try this symmetrization and anti-symmetrization. So let's remove this for now. Okay. So do you understand essentially what this anti-symmetrization is doing? Okay. So whenever you don't understand, again, follow this rule. So obviously you won't be able to, you won't know everything, right? It's not possible to know all the functions, all the operations. It's not possible. It's not possible for anyone to know it. So every time you want to know what this does and what is the syntax, okay? So always try to okay. So always try to do this. That's the first thing that you should try. So at least you know the syntax and you know what it does. So essentially what it's going to take is the expression. So here, this is your Riemann tensor. And anti-symmetrizes the expression with respect to the indices that you're giving. So now you know I'm giving this 3 ABC indices. So it's going to write down the anti-symmetric expression of this Riemann tensor. Okay? And that's what it's given here. So you can see that it's just going to do the anti-symmetric, it's just giving you the anti-symmetric terms here over ABC. Right. So okay, this is what I get. So I simplify it. There was a 1 over 3 factor. I took care of that. So took it as a common, and this is what you get. Now, if I don't put, so this is obviously one index is upstairs. Now, if I put all the indices downstairs, it has more symmetries. Okay, and that's what I'm going to see here. So again, let me remove. So here I'm not giving any indices at the end. If you see the syntax, so it means that it's going to take anti-symmetrize over all the indices. So this is what it is. I can always simplify it, or 2 canonical or simplification, whatever. Let's try simplification. Okay, so this is what I get, and I here. Is this okay, you guys? Again, I can take 2 of the indices and do the same thing. I get back this. So again, try this out. Try to write this down, whether this is exactly what you get or not, and you can always compare the results. So I wrote this for different combinations. So I'm anti-symmetrizing over the first 2 indices, I'm anti-symmetrizing over the last 2 indices, and see what the result is. Okay. Now, you can look at the symmetrization. So same Riemann tensor with all indices down. I'm looking at the first 2 indices. So this is what I get. Okay. Now, if just looking at this, you know that these 2 terms are like the same. You can just, this is just the negative of the other. So this is going to, so if I add 2 canonical, It's going to be 0. Okay? Same for the last two indices as well. Any problem, anyone? Okay. Why is the number going down? The participants, is this the same? Is this what you have converged to? Okay.
These are the participants actually. Others were there, those were here. These are the
Okay.
participants.
Maybe earlier it was in a small amount, so it was filled back.
Okay. Oh, we have a 20. Yeah, that's fine. Okay. Now, let's try to again. Oh, okay. So these are expressions that you might know of. I just tried to write it down and show. So what I've tried, it's not like I have to go through each and every cell, but what I'm trying to do is for different results which are known, which look into the symmetries of Riemann tensor, I've tried to show that it actually, if you can write down properly, it actually works. Right, so I'm not going to spend a lot of time here. I think I wrote this before. So these are again contractions. So now, if these are the same indices, it's obviously going to 0, and that's what I've shown here. Not important. Right. So the reason why. So now, if you have a combination of Ricci and Riemann, now this is one is symmetric, one is antisymmetric. So if you multiply one, if you take the product of a symmetric and antisymmetric, and that will again go to 0, and that's what is shown here. So this is Riemann and Ricci, same for Riemann and Einstein tensor. Okay, so these are all symmetric tensors. Okay, so there's a reason why I showed this. I'm forgetting now. Oh, sorry. Oh, right. So the reason the reason I wanted to show this is, if you see in the beginning when I defined the manifold, I defined just 4 indices. Maybe you will need more indices later. So in principle, you can define multiple indices from the beginning, and that is helpful. Or else what happens is, if you think like, okay, I can just add in more indices, that's not going to work for you. So we are defined up to D. Now E and F is going to give you errors. But what you can do is, you can add on to the last index. So D, you can then add to it, you can add D1, D2, and go on like this, and that's all fine. So again, this is the Riemann, Ricci, and the Levi-Civita.
I didn't get that. So you need to define it
In the beginning, yes. So the idea is all the indices should be defined. Now I defined 4 indices, and it was working fine for me. But right now in this expression, I needed a little more. So I can't just write E and F. That's going to give me some error. But what I can do is, I have the last index was D. I can extend by saying, and this you can look at any other expression as well. Like if you look at the tutorial 1 also, when it expanded, when there was a large expansion, what it does is, it adds to the last index, like D1, D10, D11, something like that. So here, that's why I've taken the additional indices to be D1 and D2.
that works.
That works.
You don't have to
Yeah, you have to again, you don't have to define a manifold again, the indices again. Right. That's what I wanted to show here. And the other thing is it's a Riemann-Ricci-Levi-Civita. Again, the product of all this should go to 0. Okay.
Now, what's the hold to null? We'll discard that.
Yeah. That's giving you a null result. Okay. So now we want to go ahead with the contractions of the Riemann tensor to get Ricci tensor, Ricci scalar, how to get the Einstein tensor. Okay, so so you can define the Ricci tensor as I said when you in the last tutorial that when you define the metric, all these tensors you can get for free. So when you are getting the Ricci tensor, this is your Ricci tensor, but you can get the Ricci tensor by contraction of the Riemann. So the general sort of definition is you contract the second and the fourth indices, and that's when you get the Ricci tensor. But depending on whatever convention you take, if you want to contract the first and the third, then also you can get the subsequent Ricci tensor. So that depends on you. Now the Ricci scalar, you also get it for free, but again, if you want to contract the Ricci tensor, you get the corresponding Ricci scalar. Similarly, you can define the Einstein tensor. You anyway get the Einstein tensor for free when you define the metric, but you can, in principle, define the Einstein tensor. And there is this function called Einstein to Ricci. So even if you want how the Einstein tensor, the expression of Einstein tensor should look like in terms of Ricci, Riemann, and everything. So if you just give this expression called this operation called Einstein to Ricci, it will give you this r mu nu minus half g mu nu r. Okay. So again, you might find why this is important. There are a number of operations which will become important because when you do calculations, you need the expressions at different levels. Maybe I need the expression at the level of the metric. I need the expression at the level of the Christoffels to do computations, right? So you need to know, you can always convert from a given expression to, you can go down to, say, from Einstein, you can go down to the how it is in terms of Ricci, how it is in terms of the Christoffels, how it is in terms of the metric. So you can always get that. So as you know, it's always a second order. Einstein's equation is a second order in the metric. So you can always go down in the expression. Okay. There are already a couple of questions. Should I just take it? Okay. Similarly, I went the other way around. From the Ricci, you can go to the Ricci to Einstein. And so here you can see that what I've given is r mu nu minus half g mu nu r. If you want it to be in Ricci to Einstein, what you get is when I'm not doing the simplification, it's just going to convert, right? So it's going to give me a g mu nu minus half g mu nu r. But again, obviously there is a g mu nu r here, g is symmetric. So when you use 2 canonical, you will just get the g mu nu. So make sure you know all these steps. These are very important. The operations, you know all these operations, and you're doing it. Okay? Or else your expressions are going to get really big, and you will, I will show this later. The expressions can look horrible, but when you put all these simplifications, it might just turn out to be 0. Okay. Okay. Similarly, you can define you anyway get the while tensor, And if you don't remember how the while tensor looks like, what is the expression of the while tensor, you can just do a while to Riemann, and you can get it in terms of the Riemann-Ricci tensor as well as the Riemann-Ricci tensor as well as the scalar. Sorry. And as you know, if there are two indices, if the two indices are same, in terms of contraction, it goes to 0. You contract the first and the third indices, it goes to 0. You can even define, this is something that you might need, the trace-free Ricci tensor, and that's what is defined by TFR, TF Ricci. That's trace-free Ricci tensor. Again, you can check whether it's really trace-free or not and look at the trace of it, and you can see that, okay, this actually is 0. Okay, but if you want to know how a trace-free Ricci tensor actually looks like, you can go from trace-free Ricci to Ricci, and you can see that this is this 1/4 factor which is there. R mu nu minus 1/4 G mu nu R. Okay. Now, xTensor, you know that there are different ways to express or the Riemann tensor in terms of the Christoffels. What the xTensor uses is the one that is given in Wald's book and not the one which is used in Hertel or Sean Carroll's book. Okay, so the definition that it gives is this particular one. Again, as this is what I wanted to point out. See, it needs an extra index. It uses D1 here. Okay, that's the same thing that we were trying to do earlier. Okay, so again, you can write down the Ricci in terms of the Christoffel, the scalar also in terms of Christoffel, as you can see here. Now, this red parenthesis just tells you that it's not a tensor but a scalar. Okay. Again, Einstein tensor, you can use a combination of it. So from Einstein, you can go to Einstein to Ricci, which you have done earlier, and then again Riemann to Christoffel. So it will convert the Ricci tensors into Christoffels. Again, you will see this parenthesis in red, which just means that this is your Ricci scalar. And so it's a scalar quantity, so that's why it's given in red. And similar things you can do for while. Again, see, it looks extremely horrible. But if you want to do computations, there will be, in certain cases, if you know things will go to 0, if you just use, like I can write down, so I know that this should go to 0, right? So in principle, it can look very horrible. But here, just another thing, always remember these are all tensors which are defined, okay? So I did not have to use this 2 canonical and all these things because all this sort of rules will already be implemented to this. So sometimes I don't have to use 2 canonical or simplification. It will anyway simplify. But if you are defining something, then you have to use, so if you are using a combination of Ricci, those identities, and then you have to use 2 canonical. But if you're just using, say, Riemann tensor, and not a combination of Riemann tensor to prove that all the identities, in the Riemann tensor, all these rules are already implemented. So you do not have to really use 2 canonical for. Okay, so yeah, this is again, let's remove this. I don't think it's required. Yeah, so this is, I've mentioned this before, but let me mention this again. So this is how we define the commutations of the Riemann of commutation. Yeah, to define the Riemann, this is how we use the definition that we use. But in Hartle or Carroll, this is how they use the definition. And these are the differences between the two definitions. So this R is the definition that we are using.
And this is the curly R is the one which is used by Carroll and Hartle, and these are the differences between the two. Okay. So taking a covariant derivative, this is something that we learned in the last tutorial. So if you take a double derivative, that's also possible. There's this. This is something that I did not tell you in the last tutorial, but I updated it in the notebook, that you don't have to, if you want, use the symbol at. Okay, you don't have to use square brackets. You can just use at, and that should be fine enough. So now, if I want to define, if I want to apply this, so this is how I can write down this commutator, right?
I can use this rule called sort the covariant derivatives. Okay? So it's going to apply this particular rule, and you will get this. Okay? So that's your sort cov Ds. Now I can do this with the other definition that I defined, that I said, and is so I'm just changing
So what does this add that it does? I know I missed
at.
this.
So it's at. So it's basically, in principle, you can write the covariant derivative. If you want to apply it on something, you write a box or P. You have to use this square brackets. Now, if you have to say, I have to do another one, okay, and I have to keep doing this, okay, rather than doing that, it's much easier to write at this, at this. So that's just a notation. This seems to be an easier notation. So because you have to keep track of the boxes, of the square brackets, not boxes. So remember, maybe you won't. So how we defined this sort of vectors? I think we defined it as to be antisymmetric and no. What I'm talking about? No. That's for the mixed tensors. No, I'm talking about this ones. So F, we defined it as antisymmetric, and then I did not do it for the other one. Sorry. I'm making a mistake somewhere here. No, this is just the upstairs and downstairs, so the minus sign comes in because of that. So now I can do the same covariant derivative on rank 2 tensor, and this is what I get. Now, if I want to do this sort of commutation, so I can even use this expression called commute convds and give grad A, grad B, VC, and over the commutation over minus the B and A, these two indices. If I do that, this is the expression that I get. Okay. Now, you know that del mu g mu nu is equal to 0, so you can, this is what you can see here. Apply the covariant derivative on the Einstein tensor. Okay, so I asked you to, last tutorial I asked you to look at the Bianchi identities. I don't know whether you guys actually looked at it. But you can, so I tried to show that the first Bianchi identity, so you can, this is how it looks like. If you add in all these different rules, so from Riemann you want to go to Christoffel, from Christoffel you want to go to the metric convention, and then if you apply to canonical, it should go to 0. So what I wanted to show is this. Okay. Things get a little bit horrible. Now, if somebody gives you this, you're not going to solve the problem for sure. Okay? You're going to leave and go. But then you can just use 2 canonical, and it goes to 0. Okay? So here you already know all these things, so it will be easy for you. But if, say, I'm trying to solve a similar sort of a problem in some alternate theories of gravity, then things will look really horrible. And if I know how to put the rules properly, then at least at some level I will get a tractable sort of expression, which I can then look and understand what's going wrong. Okay. So similarly for the Bianchi identity, second Bianchi identity, I don't want to really. It's the same thing. If you see how it looks like, I don't know whether any of you solved this identities by hand before. This has not been done yet. The Bianchi identities yet? Not here. Any GR course you haven't actually looked at the Bianchi identities? Yeah. Okay. Okay. But the main reason this particular tutorial, sorry, this is not required. What I wanted to show is how, if expressions are something that you don't know what to do, then how you should apply different types of rules, which is applicable even in Mathematica. But like you know of things like this, right? How you set something A equal to B, or A colon B, colon equal to B, what all these things mean. So here, this is assigned this particular value. This basically means that this is a dynamic allocation of this. Like B is dynamically allotted to A, which means that as B changes, A changes. Here it's not dynamic. It just becomes A is B. And there is something which is called substitution. Okay? So these are things which are anyway used in Mathematica, but sometimes it doesn't work out very well when you are doing tensorial calculations. So there are certain operations which are included in xAct, but does something similar. Okay. So what we are going to define are again a few tensors which we are going to manipulate. So temp t1 it will print as small t. Temp t2, which is a mixed tensor, will show up as the output form is capital T. And temp t3 is again a one-form tensor of which is Q. Right. So not required. Symbols this is protected. Let's try some other number. I have to figure out why that is the case, but anyway. Depth tensor. What?
Manifold M4 is not defined.
M4L, no? I've defined the manifold. Why is it not defined? Oh, I've changed it to. Sorry. Okay, now let's see. Still not. Okay, let's try this now. I'll figure this out later. What's going on? Okay, so I'm defining 3 temporary tensors which I'm going to manipulate. So if so as you can see, because I defined, I'm going to, the output form for temp T4 is T. So when I'm writing this, it's going to give you T subscript A. So the first sort of substitution or assignment that I'm going to talk about is this called index set. So this is equivalent to this one, right? You are just going to substitute. Again, you can look at what an index set is. So it defines a relation between the indexed expression LHS and RHS. Evaluating RHS in advance. Okay, so it's not dynamic allocation. So I am saying that my T4 is FAB/VB, okay, and it's going to be that. That's what I'm going to set it to. So now if I write T4 minus B, it's so T4 minus B. Why it's TB? Oh, did I not run this? Sorry. Yeah. So that's what's going to happen. Okay, so I'm setting my temp T4 to FAB/VB. So, and this cannot change. So I'll tell you what I mean by this cannot change when I'll use the other rule. So now if let me evaluate some expression. So I'm giving temp4 minus A, temp4 minus B, or T A, T B, G A B. So I'm contracting. And so if I remove the contract metric, this should give me this, right? So FSE VC, FBD VD, and GAB. Now I can always use contract metric and do the contraction. Okay. Few other things. Now the interesting thing is, see how it has been defined. So, okay, sorry, I did not tell this. So, you know this, if you know Mathematica, you know this underscore, right? It's going to take any argument. This is how, say I'm defining a function and I give a set of arguments. It's not like this, that's the argument that you have to give, right? That's you can then, when you declare the function, you can always say like, okay, if my function is, if I define a function given xy, it's not like when I'm trying to evaluate it, I can give any value to it, right? Xy can be whatever I define it, I can give 1, 2, and it's going to take those arguments, right? So similarly, you know that how when you define functions in Mathematica, you give this underscore, which basically means the argument can take any value, or whatever value you are going to give at the time of evaluation. But remember one thing, it's minus A, okay? So it's downstairs. So if I give T4, the contravariant counterpart of it, it will not give me anything. It will show up as TA. Okay? So you have to define things properly in proper like indices. Like if I'm going to give the covariant form, what is the expression? I'm going to tell what the contravariant form looks like. So I have to assign things properly. Okay. So now let's do that. So what I'm doing is for the contravariant, for the covariant one, I've already assigned. Now I'll do the same thing for the contravariant one. Okay, now it's fine. Okay, the next thing which I said is dynamic allocation, dynamic assigning the values or the expressions dynamically. And this is called index set delayed. Okay, so let's take the same thing. Index set delayed. I have this function, and again the LHS, RHS is assigned to LHS. So I'm assigning this to this tensor. So let's see how it looks like. Okay. Now I can change this. I want to see whether what I can now set something to temp T3 as well, right? So I'm setting temp T3 as this particular expression. Not T3, T6. Then what will T5 become now? Okay. Now I can set something different. So let's T6 be Ricci and this product of Ricci and the vector, and let me print out T5 again. I did not run this, I guess, and it gives me this expression. Okay, so this is dynamically I can allocate. I can keep on changing the expression, and it can dynamically allocate. Okay, so the next thing is the index rule, which is this one. Okay, so you're just substituting now. No, the previous one was substitution. This is like assigning. So say I want to assign VA as GAB XP. And if I remove the contract metric here, what I get is this. Okay? If I can contract, this is gone. Okay. But since this you're just assigning that value, like earlier if you would have printed this, because I had already substituted this with some expression, it would have given me something else. But now if you just print VA, it doesn't change, it just gives you VA. Right. Rather than assigning, or you had this thing in Mathematica, which is escape, arrow, escape, right? That which is, say, in Mathematica you use it as, right? This is what you get. Here, what you are trying to, here you can just write box, right T arrow, and you get this. So this is same as setting an index rule. Okay. So if you do that, it's the same thing. So you can get the same thing here. So if you, that's just a different way of, different notation. Okay. Now this is a new thing. I did not actually know this, that you can choose where to apply the rule. So this is something that I learned a couple of days back when I was checking. So but I have some issues. I haven't figured out certain things. So maybe you guys can look at it. So, but let me at least tell you what you can do, because it's interesting. But I haven't figured out everything about this. So say I have this expression. I've written this particular expression, which looks basically like this. And so I can use, so okay, firstly you have to again load this package called express manipulation. And this is how you can load it. It's already there in xAct. So you don't have to install it again. You just have to load it. And you are writing this particular expression, and then you can use this function called color terms, and it will tell you the different terms which is there. Okay. Now say I want to apply a particular condition on one of the terms and not all the terms. Okay, not one, multiple, whichever, but not all. Okay. So say for example, if I want to take this expression and do this particular operation that all the Riemann Richies should go to Christoffel. So this is what I get. Okay. And I'll tell you why I've put this, I've given a name to all these things. Now, what you can do is, you can do the same thing for any one of the expressions. Okay. So right now I want to do the same operation to expression 1. So to the first expression on the left, which is this one, right? So this is the expression, this is the function that I want to do. You can look at again the syntax for it. This is the function that I want to do. So you use this this thing called map_at, or this function called map_at, and then you say like, okay, this is the operation that I want to do, Riemann to Christoffel, and this is my actual expression, and I want to do this just on the first. Or only the first expression of this entire expression, right? Or the first term of this entire expression. And I'm getting this. The only problem is I don't understand where the while is coming from the first expression. This is what I'm not being able to figure out. And then what I did is I individually did this to all the three terms, and I gave them some names. So essentially, if this is the total thing, and these are the three terms, then this minus all of this should give me 0. That is not happening. So if you can figure out this, that will be great. Hello. But it seems to be very interesting the way you don't have to apply the rule to the entire expression, but you can choose which of the terms you are going to apply. It seems to be an interesting thing, but I haven't seen this before, so I have to look at it properly again. But if you can figure out, please let me know. Okay. Similarly, as I mentioned, it's not like you have to apply it to just one of the terms, but you can apply to multiple terms. The syntax being this curly brackets, you give multiple curly brackets and you specify which of the terms you want to apply this on. So if I can say like, okay, I have some 10 terms, I can define which of the terms I want to apply any of these rules. Okay. Oh, and also it's quite interesting to find patterns. So I want to find out, it's a really long expression. I want to find out a certain pattern, which we always look like. If we know the patterns, then we can apply all these rules and stuff. So this will, so you can, in the expression, if I want to find out where are the Riemanns sitting, okay, so it will tell me where it is. So it will point out where the Riemanns are. So it seems to be quite nice. But I have to look at this a little better. Okay. So again, you can tell, oh, I want to again apply this operation Riemann to Christoffel for this particular expression, and not the entire expression, but this particular term where so I'm going to define the position as the expression where I find the Riemann. Okay? Only there apply the operation of Riemann to Christoffel. Else don't. Okay? Right. And the last thing, as I mentioned, this is, I hope this is the last thing. Yeah. The last thing is this make rule. Some of the rules are already known, right? And some of the things that you can you can define rules on the fly. And say this is one of the rule that I'm making a rule that this vector, I'm going to, so let's again see the documentation for make rule. Okay, LHS are RHS, these are the two arguments that you have to give, and gives a list of delayed rules with left and right hand indices as given by LHS and RHS respectively, but moving indices to consider all possible equivalent rules. So I'm going to substitute this particular expression to VA, to this vector, right? So now, given this rule, this is going to be this, right? So VA is going to change to RAB UB. Let's make it a little more complicated. So this is my new rule that this vector is the covariant derivative of this tensor product of these two other vectors. So again, I can apply this rule, leave out the simplification, and I get this expression, and then I can simplify it and get this. Okay? I want to say that, okay, in this expression, so let's look at this again. In this expression, I want to add another rule that the covariant derivative goes to 0, okay, of UB goes to 0. So if I add this additional rule here, it looks like this, but as you can see, if I simplify, this should go to 0. Do you really understand that it should go to 0? Do you know why this should go to 0? I want this answer in the next tutorial. So for now, let's. Just two questions at the end. So we have using this whatever we taught today about how you can set rules. Let's try to derive the geodesic deviation equation you have learned today. So you have done this calculation by hand. So let's see how you can use all the rules to get this. Okay. So I have set. So what you have to calculate is this, the congruence, and I have also set all the rules that you have to put, that you have to use. Okay. So you can set all these 5 rules and then calculate this. Okay. And similarly, you have to show this particular, You can do this as well. Okay. Thank you.